Okay, good afternoon, everyone. So today I would like to continue on our journey to AI. So I guess since the beginning of the class that we met, we haven't really touched on the AI yet, right? We have been learning about Python, basically just programming. But I guess from now, it's going to be more, the actual core concept of this class. So why don't we start from, multiple linear perceptron. So that's going to be another way to call this one is the artificial neural network, or ANN. But nowadays, I think it might be best to call it MLP, so multiple linear perceptron. So that will be kind of like the first thing, the first building block for all of the AI things that we're going to learn, like image like image processing, language and things like that, all based on the concept for this MLP. So that will be a good starting point for that. And then we'll come back to Python. I hope today or next week, the latest. Okay, so we're gonna, based on this particular lecture that I post, please download it if you want, if you can. So I'm gonna just download it too. Okay, it's in here. Hopefully it's working. Yes, okay. But the font looks a little bit weird. Let me see. Okay, it's not too bad. Okay, let me just pull this one down. All right, so we're gonna go for, the first thing is the, what I would consider as the distinction between the classical machine learning and also the kind of like a deep learning era, okay? So what have you been learning with Ajahn Vimalin so far? I would say that that would be considered as the classical machine learning, meaning that it kind of happened before the boom of the AI thing that we have experienced, right? But don't take me wrong, don't get it wrong, okay? Because when the term classical might signify that it's old and ancient, but that's not the case. So classical machine learning is still relevant today, and it's actually might be a better choice for some of the work, some of the context, okay? Mainly for the performance and also the efficiency, okay? So classical machine learning is usually very small, kind of like it will be less computational demanding. Sometimes can be much less computational demanding, and it might be the good choice for your problem, okay? And if you want to go for that classical machine learning, usually the gradient boosting would be the state of the art, meaning that it's the most kind of like the most famous methods for that, okay? So anything with gradient boosting or the tree, kind of the tree model, okay? And in Python world, the library for that would be XGBoost, CatBoost, and LightGBM. And even if you read the paper that comes out like nowadays, they're still using all of this model as the benchmark for the classical machine learning model, okay? So nothing wrong with this, and they are very relevant today, okay? But then we're gonna go for something that people might relate to, like AI. So for me, it would be something like deep learning, okay? And for that, we're gonna start with artificial neural network, or MLP. Something that I would like to call it nowadays. Okay, so this is the foundation for deep neural networks. Okay, convolutional, that's for the image, and then for the sequence will be the LSTM, and then the transformer network for the language. So anything AI related, you gotta know this concept, okay? All right, so let's deep dive onto ANN, or MLP, as I would like to call it nowadays, okay? So the first thing is, if I give you this data, one-dimensional data, very easy, X and Y. Also notice that this data is a bit noisy. Okay, so how do we fit a line to this data? Okay, if you don't know any concept about ANN, you can just use mathematical function. Okay, so essentially what you're doing is we are going to write the y as a function of x. right? The mathematical notation for that, okay? And you can simply just use any mathematical function that you know. For example, polynomial would be kind of like the first choice that you might want to try, okay? Or if you notice that this data looks sinusoidal, it has some up and downs, then you might want to use the sinusoidal function like sines and cosine. That would be appropriate, okay? But then if your data is very, very high dimensional and you don't even know what it looks like because you cannot even visualize it properly, then you might need something that's a bit more general, and that's why we turn into something like this, artificial neural network or multiple linear perceptron nowadays, okay? And when I think about A and N, I only think about it as a function. So whether you use this or this or this, it's just a matter of a function. So it's a function of the input. So it's like you can think about it as a black box, a box, right? This box, you input some data into it, and then it split your output. That's all it's doing, okay? The output can be a number, like a continuous number. That would be called regressions. Or the output could be the class label, like 1, 2, 3, 4. And that would be called classification, something that I believe you have done this with Ajahn Vimalin before. So all of this, just a function, okay? All right, so I guess what's the nice thing about artificial neural network is that it's very, very flexible, okay? I usually think about it as like a Lego, okay? Meaning that you can, there are building blocks, right? But then this building block, you can use it to compose or build any type of things that you can imagine. And that's the same thing with the artificial neural network. Like the building block, it's called node. Like this node, you can take it and you can build it anything. And even nowadays, when you have like a big LLM, still based on some of this, a lot of these concepts still relevant to that, architecture. So yeah, and all of these building blocks, what I mean is like this. Okay, so a lot of things that I guess you will pick up, from starting using it. Okay. Okay, and the fact that I try to introduce the word multiple linear perceptron or MLP rather than ANN is the fact that before this architecture was based on the biological neural network. So it's actually based on the biological architecture in the cell, like a neural cell, right? But then nowadays, that distinction or that comparison is no longer relevant. And even for the architecture, like convolutional neural network right nowadays, they're not even based on like biological structure anymore. So that kind of distinction I think doesn't work nowadays. Although the name kind of stuck, so some people still call it the ANN, right? All right, so when we talk about this MLP, then I think I should call it MLP. Then we're gonna think about it as the layers, okay? So there are, and one layer, you can think about it as like a sequence of operations, okay? So the first thing is we're gonna have input layer. So you can think about as the data coming in, right? It's gonna hit this, layer first, okay? It's actually just a function. It's the mathematical function, okay? But think about it as a layer, okay? And something is gonna happen inside, okay? And then that will be hidden layer. So you can have as many hidden layers as you want, okay? And if you have more than a couple hidden layers, we're gonna call them deep learning, the deep architecture or deep neural networks, okay? And then the output layer is gonna be the last layer that split out the y value, okay? So again, this thing, the whole thing in here, just a function, fx. That's all it's doing, okay? No matter how complicated it is, this is a function, okay? Okay, so let's kind of peel into a particular node just to see what it's doing. It's actually quite simple, okay? So I'm gonna start off with the node that has, all the features, which is gonna be the hidden node, okay? So when I say hidden node, I mean this particular, oval right here, it's gonna translate into one of this in here, So if I were to consider one of this in the hidden node, and then I want to see what it's doing, then this is what it's doing. Okay. So inside, there will be two main operations in here. Okay, so these are the operation. Okay. These are the input that come from the previous layer. Okay, so think about this. If you have a nodes in here, then it will accept all the input into this node. So that is the X that I mean from the other page. Okay, so this is from the previous layer. Okay, not the input from the outside. Okay, and then this is the output that goes into the next layer. Okay, again, if I were to go back to my picture, this node is going to split the input. It's going to give the output to all the nodes to the next layer, right? So actually, it's going to output the same thing, right, into all of the nodes in the next layer. So that's how the connectivity is designed. Okay, so this is this part right here. Okay, but then so you can think about it, this. This is actually just another function, right? Maybe I just call it f prime. Like this is another function, right? Something goes in, something go out. That's another function. Okay. But then what's it's doing inside? There are two main operations. The first operation is called the net input function, right? It's another function. But this function is actually just a linear function. Okay. So we're going to write this x, all of this. Okay, so all of this is actually this guy over here. We just write it as the vector notation. It's more concise. Okay, and then the rest of the value w is actually this guy over here. It's called the weights. Okay, so the weights is something that already exists before you used it. Okay, either this weight can be just randomly guessed from initialization, or this weight can come from training. So when you train the network, this weight is going to be determined throughout this optimization process. Okay, but this weight has to be there before you used it. Okay, and also there's going to be another bias right here. Okay, so this one, similarly, it has to be there before you use it. So weight and biases are called the parameter. So the parameter is something that you would initialize at the beginning, and then you will optimize it throughout the training or learning process. Okay. Okay, but as you can imagine that this is called the linear function, because this is just the the weight times the input. So like a slope times the input, right? And plus the intercept. So some people call it the slope and the intercept, because this is almost like a linear regression. Okay. The things that will get out is actually this value over here. It's called z. So z is just the result from the linear function, or you can call it linear transformation too. Okay. But then this z over here is going to go through another function called the activation function. And again, the name might be a little bit unfamiliar. The name comes from the biological neural cell, because in our neural cell, we do have the activation cell in there. So that's where the name is kind of a stage here. But you can think about it as the nonlinear function. So this one can be your choice of nonlinear function. Although there are a couple ones that has been used so far, and there are usually we just stick to the one that are the most performance. Okay, so we plug the z into your nonlinear function or activation function to get the result, which is called v. And then that's all. And then this node is going to transmit this output into all the nodes in the next level. Okay, so that's all it's doing. And as I will mention many more times in here, like even the most complex architecture nowadays, like in the LLM, they're still using something like this too. Okay, although there are many other components with it, but a lot of the computations can come from this type of functions. Okay, so we go through some of this right in the hidden layer. The node from the input and the output is actually going to be the simplification of what we just learned. Okay, so let me check it out. Oh. Oh, okay. So, but then this one, I just skip this page because this one is actually, yeah, you got to learn about perceptron, but we kind of skip that. Okay. But then the nodes in the input. Okay. So this one, imagine that I'm taking a look at some of these guys in here. Okay. It's going to be the simplification of what you just learned in the hidden node. So this one only has the, it doesn't have any weights and biases. So the weight and biases is going to be equal to 1 and 0. So this one doesn't change, okay, fixed. So that means that your, I guess, linear transformation is just going to be boiled down to just one-to-one mapping. So, so essentially you don't do anything. Z equal to X because weight is 1, B is equal to 0, okay? And then the activation function also is going to be just mapping function too. So this one is very easy because the output, okay, it's going to be equal to the input, okay, which is kind of trivial, right? But we need a node, you know, in the layer in our architecture to receive the input. That's why we write it like this, right? But you can think about it as just not doing anything too. Okay, and then the output node, which is the last ones in here, like these two guys in here, it's also going to be just a little bit more complicated, you know, not that complicated. So we're going to keep the linear transformation parts from the hidden node. Okay, so again, Z will be equal to the weight, you know, times the input. You know, this is the input from the last hidden layer. Okay, and then we're going to add with, to it with the biases. Okay, again, remember that all of this you have to, this has to be, you know, present before you use it. Okay, either from initialization or training. Okay, but then what's different from the hidden node is actually this part. So this part is simply just the mapping function again. So no nonlinear function. Okay, just one-to-one mapping. Okay, so that means that your output is going to be equal to just the Z value. Okay, that's all. Okay, very simple. But you know, with this deceivingly simple operation, you can produce, you know, a lot of things in here. You can make, you know, a lot of prediction. You can fit this to all kinds of data because you do have the choice for how many nodes are in your hidden layer and how many hidden layer are you going to have. And that flexibility make this whole architecture super, super flexible. And that's why we call them universal approximator. Like this thing, it really can be as complex as you want, and it can do anything. Like even this one can also do image. You can do language, you do anything, but it's just way overkill in terms of the computational expense. That's why people have, that's why, you know, there exists another type of architecture like convolutional, like transformer. All of those things is created because if you only use this type of architecture, you can run out of compute very, very fast. Okay, but this one pretty much, you know, technically can do all kinds of things that we are that AI can do today. Okay, all right. So, you know, if we work only with just a simple nodes and a small number of layers, actually we can even write out what the mathematical function this black box is. Okay, so the simplest nodes or architecture that you can do with MLP is actually just one node per layer and then just input and output. So no hidden layer. So that's the simplest thing that you can do. Okay. So let's think about, you know, what the transformation is going to happen in our architecture. Okay. So first we have the X that goes in. Okay. So X goes in. And the first linear transformation node from the input layer doesn't do anything. So you're going to end up with just Z that is equal to X. Okay. Remember that the input layer is actually super simple, you know, just one-to-one mapping. Okay. And then activation function in the input layer also does not do anything, just one-to-one mapping. Right. So again, the output from the input node is going to be equal to the input value. It's the same thing. All right. A little bit you know, the part that is a little more complicated is the output layer because the linear transformation process gonna have these non-zero weights and biases, okay? So we're gonna have some transformation called Z, okay, which is different from the input. But then the activation process is actually just one-to-one mapping again, okay? So in the end, what we're gonna have is that this thing is gonna equal to this one, or I should say here, this, and this one, the same thing. Okay. Okay. So if I were to collect all of this processing or transformation and then put them in terms of the last output and the input from the beginning, then I would get something like this. Okay. So Y, which is the output from this this architecture, is going to be equal to the weight from the output layer times the input, and then plus the bias from the output layer. Okay. So keep in mind that there are parameters in here, okay? And this one, the parameter part is actually this guy over here, this one and this one. This is called the parameter, okay? And again, you should recognize this one right away, right? This one is just a straight line, the equation for the straight line, okay? So if I were to use this architecture, okay, and I use the library in Python, I did that too, okay? To fit to this data. This is the best model that can come out from this data. So I took the architecture and I give it this data to learn. Okay, you will go through the learning process later. But when I train this architecture with this data, this is the best it can do. Best meaning that this one minimizes the error. Okay. And I mean, it would come as no surprise that you are seeing the straight line, right? Because this one simply just the linear equation, okay? All right, we can do much better than this. So let's make it a little more complicated, shall we? So I'm gonna add in a hidden layer, this one, okay? And this one, you're gonna see that we're gonna start to have nonlinearity in our output, okay? The input layer stay the same, so I will not go into more detail. So essentially, the output from the input layer is going to be equal to the input exactly. It's not doing anything inside, okay? But then the hidden layer is going to comprise of first linear transformation, right? And the activation function. And this one, I do have many choices, but I'm going to choose the classical choice, which is the sigmoid function. Okay. Let me show you what the sigmoid function does. Okay, so I'm going to search for sigmoid function. Okay, this is how the sigmoid function looks like. Okay, so think about this as the input, x, and y as the output. Okay, and what the sigmoid function does, it's called squishification. It means that whatever goes in, you see that the number that goes in actually lies along the real axis. So your x can be anything from negative infinity to infinity, okay? But notice the output. The output is actually capped around 0 to 1. So this function is used because no matter what the input is, the output always going to be 0 to 1. And that makes the numerical during the training more stable, because we don't want the output to be really, really huge number. So this one kind of limits the output to 0 and 1. That's why this type of functions is chosen. And you're going to see that actually this one is very, very conservative, meaning that it's too stable. And later on, we're going to relax this type of function to make it a little bit more, I would say, more exciting or more dangerous. And that's going to speed up our computational computation a little bit. Okay. Okay. So that's the reason behind this choice. Okay. Again, this is the type. This is the functional form of the function. Okay. And again, you got the output from the hidden layer. Okay. And this one's going to go into the output layer, which going to go through this linear transformation, and then also just the mapping function for the activation function. Okay. And if I were to collect all of this operation and write it in terms of the final output, and the first input, then I will get something like this. Which, I mean, you can kind of imagine that right now, it's a little bit more complicated than before, right? We're still using, MLP, but we changed the architecture, and now we got some nonlinearity in our function, right? And if I were to use this particular architecture, and I train with the data that I showed you from the beginning, this is what I got, okay? This is the best fit this architecture can do with this data, okay? And as you can see that now we don't get linear line, the straight line anymore, which is good, right? Our data is quite non-linear, so you can make your network a little bit more complicated, right? And a good, indicator of how complicated your architecture is, it usually comes from the parameter. Okay, so right now we have 4 parameters. So keep in mind that the parameter is weights and biases, right? So if I go back and I want to count the number of weights and biases, then it will be something like this: 1, okay, 2, 3, and 4. Okay. When we have more parameters, the model can be more nonlinear. Okay. All right. So this one, I mean, we can all agree that it's not that good. Okay. So let's move on to something a bit more complicated. So this one. So this one, we have one, the input layer and the output layer. Same thing, right? But in the middle, you can see that now I'm stacking 10 nodes in the hidden layer. Okay? So that means that this particular, the output from this input layer, it has to be fed into all of these nodes in here. Okay? And in the end, all the output from all of these nodes has to be fed into all of this. Okay? So you can kind of see that it's called a fully connected architecture. Okay? And I'm going to stop, expanding one by one because it's going to get kind of ridiculous, okay? But you can kind of take my word for it that the final equation, if I were to write all of this operation in terms of the final output and the first input, then I would get something like this, okay? And keep in mind that this one has the summation. So that means that there are 10 terms that looks like this. All of them will have different weights and biases, right? And then also the last, bias too, okay? So first let's see how, how complicated this model is by counting the number of parameters, okay? The input node doesn't have any parameter, so this one is going to be 0, okay? But then all of this, in the hidden layer, we're going to have 2 parameters each. Okay, so for each node in the hidden layer, there's going to be 2 parameters. All of this. Okay, so as you can imagine, that the hidden layer should have 20 parameters. Okay, 2 each, and there are 10 nodes in this layer. Okay, but then if you think about the output layer, okay, you have to think about this because the output is the linear transformation of all the input. So you need the weight for each of the input. Okay, so the output layer actually, the output node, okay, actually accept the input from the 10 nodes in the hidden layer. So there are 10 input. So for each input, you need a weight for each input. So that's why I'm writing W1 to W10. Okay, you need different weights for each input from the hidden layer. So that's why all of this will give you 10 parameters. Okay, and then plus the last bias. If I'm count all of this, I should get 31. Okay, so this is how you would count the complexity, how you would, judge the complexity of your model. Okay, and if I were to train this model with the data that I showed you earlier, then this is actually the fit. Okay, so as you can imagine that right now, the same type of model, but different architecture, now we can make it a lot more complicated than the straight line that we had at the beginning, right? However, I don't have to stop here, okay? I mean, if we can see something like this, I think this is a good model, okay? It's relatively, it fits relatively well, but not too complicated, okay? But unfortunately, we don't have the luxury of seeing something like this in the real data. So you might be tempted to make it even more complicated like this, okay? So this one, again, we're going to have the same one input node and then one output node, right? But then in the middle, there are way more nodes than before. Okay, so we're going to have two hidden layers, the first and the second hidden layers, okay? And for each of the layers, there are 64 nodes. Okay, so that's quite a lot of computations, right? Okay, let's think about this. Okay, so I mean, I count the number of parameters for you, but let's kind of break it down, how I came up with all of this number, shall we? So first, you can imagine that each of the nodes in the first hidden layer will have one input from the input layer. So each of them only required one weight and one bias, okay? So two each, right? But there are 64 nodes, so there are 128 parameters. So that's how it is. So 64, I cannot write in here, but yeah, 128, right? How about this one? So this one, you have to imagine that for each node, it's going to accept the input from all the nodes in the first hidden layer. So there are 64 input that goes into the nodes that I just kind of make the square contain in the rectangle, right? So you need the weight for each of the input. So you need 64 weights for the linear transformation parts. Okay, so that's why I'm writing W1, or the notation is going to be complicated, but it's just weight 1 to weight 64 for each of the input from the previous layer. Okay, so that's 64, right? But then you also have one bias, so it's going to be +1. So 65 parameter per node, but actually there are 64 nodes. So I guess take my word for it, 64 plus 1 times 64 should be equal to this number. Let me know if I didn't calculate that correctly, okay? If this is wrong, let me know, okay? All right, and then the last one, we only have one node, but then this node actually accepts 64 input, so you need 64 weights, and then one bias, so another 65 parameter. Okay, so all of them add up to 4,000 parameters, right? And again, this model will be quite, will be significantly more computational demanding than the previous one. Okay, so remember previous one, we only have 31 parameter, and as we can all agree that this one, fits pretty well. But in reality, you don't see something like this, okay? So we might be tempted to use this architecture, which is way more demanding. But to tell you the truth, I don't think it actually fits very well. Like you see this part, this is fitting to the noise, right? You don't want something like this because you know that this one is going to be over-fitting, okay? I'm not sure, but I believe Ajahn Vimalin might have mentioned something called over-fitting, meaning that you fit too well to your training data, but it does not generalize well. And this is kind of like the red flag that if you train your model and then your training accuracy is much more than your testing accuracy, it's called overfitting. And this model is bad model. Okay, so this is kind of like the challenge when you use like this type of architecture, because it's very tempting to go for higher or more complex model, and then you can overfit your data very, very easily. And then you have to wait for it to train too. It takes a lot of compute too. Okay, so there are ways that you can kind of see this, but you have to have some other metrics to judge this. Okay. All right, so we can even go crazy like this. This is called, I can call this one the deep neural network now, because it's there's many hidden layer, right? So we can call it deep learning, right? The fancy word that people like to call it. When you do AI, I'm doing deep learning. It's just a matter of having more hidden layer. You can call this deep learning, okay? And again, I don't want to write anything more, because now I have 256 node, right? 256, 128, 64, 32, 16. Okay, I don't know why, but it just turns out that, you know, the architecture that people like to construct will have something in the order of, you know, like this, which is like a multiple of 2 for some, I don't know, historical reason. But, you know, you can have, I don't know, 71 nodes in one layer too. Like nobody's gonna, you know, flag you for that, okay? Just arbitrary. But, you know, we like to keep things in the multiple of 2, I guess. Looks nice, okay? All right, and this one, it's going to be way too complex, right? This one have about 100,000 parameter. So as you can imagine that this one will take quite a long time to compute, okay? Compared to the one with 30 parameters, right? But then it doesn't help you that much, actually. I would say that this one, it's actually not that bad, but what are you capturing in here? Like if you can see the way that the model is doing, like it has all this, you know, jagged line, right? This kind of jaggedness, it's just capturing the noise, right? It doesn't help your model at all. But then you are paying a lot of price for this. This one is way too complex, okay? So, I mean, as the moral of this story is that, you know, when I do any type of model prediction, model building, I always turn to classical machine learning always first, okay? Because classical machine learning is very fast. It will give me, you know, what type of performance or type of, you know, accuracy that I'm targeting. And then when I come to here, then I know what I want. Like I know what's a capability that I'm expecting. So I don't have to keep searching for all of this more complex architecture. I know when to stop, basically, okay? All right, so that's kind of like the way that you would, you know, judge your model, like basically it's just the complexity of the model, okay? But now, you know, in order to understand what this one is doing, you have to understand the 2 main operations in the model, which is first, prediction, or some people might like to call it inference, and then the training or the learning part of the model, okay? So the prediction, something that I mean easier to understand, so I'll start with this first, okay? So for here, we're gonna consider a relatively simple architecture. Again, I'm gonna name this one using this notation. So in is the node in the input node. Out is the node in the output layer. Input layer, output layer, okay? But then the nodes that in the hidden layer is gonna be named as the H, okay? So H1 is a hidden layer 1. But then in the hidden layer number 2, there are 2 nodes, so I have to name them distinctly. So it's going to be H21 and H22. Okay, so bear with me. So the notation is going to get a bit kind of tedious, but then I need a way to distinguish all of this so that, you know, we can be more precise when we describe this. Okay. Okay. So the network contains 2 hidden layers, and then the activation function is going to be all sigmoid for now. You know, it actually doesn't really matter here. It's just a number, okay? It's just a function, okay? And then, as I was mentioning, right, because in order to do prediction, you need the weight and biases to be present. So that's why we're going to initialize the weight and biases as the following, right here, okay? And then I'm going to just do this because it's kind of easier to write. So usually you just do random number, but for now, I'm going to just do a whole number. Okay, so the weight for the hidden layer 1, right? The weight for the hidden layer 2, right? Hidden layer 2. So there are, keep in mind that I use subscript to distinguish between the node in the hidden layer 2. Okay, so it's a bit more complicated, all right? But yeah, let's do that, okay? So 1, 2, 3, 4, 5, and 0. So all the bias is going to be 0. Make things a little bit easier to write, okay? And then another thing is I'm going to say right away that, you know, I have the observation. So this is the truth, right? The truth is that I observe something in nature that if I have x equal to 1, the truth is that y is going to be equal to 10. Okay, so that is a ground truth, meaning that if my model is doing well, you know, when I input 1, the output should be 10. That's my expectation. Okay, so that's kind of like my, I guess my hope that my model will do based on this choice of weights and biases. Okay, so if you change your initialization, then of course it's going to change the output, okay? But I'm hoping that, you know, this choice is going to be good. I'm hoping, okay? So let's check whether that's true or not, okay? All right, so these are the operation that's going to be, that is done to do the prediction, okay? I'm going to go into one by one, okay? So first, your x is going to be 1 because that's the one I want to test, okay? And I'm going to go through, so the first, remember that the input node is always the easiest. So it doesn't do anything, it's just mapping the value, okay? So the results from the first operation is just going to be 1, doesn't do anything, okay? And also the activation function, it's not going to do anything either, so it's going to be 1. Okay, so essentially, this one always going to be equal to the input. Okay, so that's all. More like a placeholder. It doesn't do anything. Okay, the next one. Okay, so the input to the first hidden layer is going to go through this linear transformation. Okay, so Z, which is the output from the linear transformation, you're going to use the input from the input node times the weights, which is 1 right here. So this is 1. Okay, and 1 is in here, okay? And then time the biases, which is 0, okay? As I was writing, just, you know, next to it, so 1 times 1, that's why it's 1. So keep in mind that it's 1 because of the choice of weight and biases, not because this is not a mapping function. It's a linear transformation, okay? So the output from that is going to be just 1. Okay, so this guy over here. Okay. Okay, so next up, we're going to feed this 1 into this activation function. And my choice of activation function is a sigmoid function. Okay, so this is the form of my sigmoid function. My sigmoid function does not have any parameter, but it's, you know, nonlinear parts. Okay. So I'm going to plug in 1. So my 1, which is this guy over here, so go in here. Okay, so I'm writing this. Okay, that's going to be equal to 1.371. Okay, so my output from the first hidden layer is going to be 0.371. Okay, but keep in mind that the nodes in the hidden layer 1 is connected to the 2 nodes from the next layer. So that's why this node has to feed 2 outputs to the next layer. That's why I have 2 copies of this number. Okay, and you can kind of see how it's go because it's going to be repeating now. Okay, so I'm going to consider the first node. Actually the next hidden layer. So there are 2 nodes, so I have to consider kind of 2 sets of operation. So the first set of operation is a linear transformation one more time. Okay, so let's consider the first hidden node in the second hidden layer. Okay, so the first node in the second hidden layer. Okay, that's it's going to be annoying to say. Okay, again, the input is 0.371, so this guy goes in here. So that's the input. Okay? But this node has another parameter called W1H2, so that's going to be 2. So this one goes here. Okay? The bias is going to be all 0 here. And you can imagine that the answer or the output from that operation is 1.462. So this is the one right here. Okay? Again, let's do it one more time so that you are more familiar with how it works. Okay, the second node in this layer, we're going to have another input, which is again equal to 1.731. Okay, so this one goes here. But this one also have a new parameter called W2H2, so number 3 here. Okay. And then the bias is going to be equal to 0 one more time. Okay. And my, I guess the result from that is 2.193. Okay. And now you're gonna start to see that there are different sets of values now, unlike before. Okay, so after the linear transformation, I have 1.462 and 2.193. Okay, and now these two numbers are going to move on to the activation process. Okay, so again, the activation process is simply just plug this thing into the sigmoid function. This guy over here, and this guy goes in here. Okay, and my results is 0.811, 0.899. Okay, and the results from this is going to be feeding into the output node. Okay, again, the output nodes will have two inputs, so it needs two weights. Okay, so the first, so again, the first input goes here, second input goes here. Okay, but then there are also weights for each of the input. So the weights 1, 4, right, goes here, and 5 goes here. Okay, and then the bias again is always 0. Okay, so and the answer for that is going to be 7.745. Okay, but then keep in mind that in the output node, the activation function does nothing. So this is going to be 7.745 one more time. Okay, so in the end, what I input is 1. What I got from this model is 7.745. That's the prediction. Okay, so you can always remember this type of operation that no matter how complex your architectures are, this is what it's doing. Like even the other type of layer like convolutional transformer, this is what essentially it's doing. Like input something and output something, usually through some type of linear and nonlinear transformation. It's just the fact that you have so many nodes that it becomes black box. But inside it's always going to be something easy or something simple like this. Okay. All right. So how do we do? Like how is this model doing, right? So as you recall that before, I was telling you that I expect this model to produce 10. But it gives me 7.75 or something, right? So with this information, we can calculate how bad the model is or how good the model is by the concept for the loss. Okay, so the loss. So the loss tells me how bad our model is, okay? And there are many ways of calculating loss depending on which type of prediction you need. So I want to start with the one that is more, that is simpler, which is the continuous prediction. Okay, so you can calculate the loss by plugging this into a matrix called the mean squared error, okay, which is just the square difference, right? The square difference between the real output, this is the ground truth, and this one is a model prediction, okay? And you are summing all over your observation. So this n is your observation, right? So maybe I have many observations, right? Maybe I have something like if x equal to 2, right? My y should be equal to, I don't know, 15. That's another observation. But then if my model is telling me, wait, this one is equal to 10, then that's just another term basically in here. So you can have as many observations. So, or you can think about it as like a row in your Excel. Like if you have the Excel as the input file, each row is your observation. Okay, so you're going to summing all the rows per se, and then you're going to take the average of it. So that's called the mean squared error. Okay. Okay, so if we only have one observation, then this term is simply just subtracting the ground truth with the prediction, and then square them, and then it's, that's going to be the factor of 1 over 1, which is just 1, right? And then that's going to be my loss. So 5.082. Okay, and this one is quite important because this one is actually what I need in order to train my model. Okay, when we train the model, our hope is that our model next time it should produce less loss. Okay, and this is essentially just the optimization problem, right? You want your model to produce the least loss, and then the things that you can change in your model is actually weights and biases. You are changing weights and biases to make sure that that number go to 0. That's your goal. Optimization problems. Okay. All right, so this is the crux of all of this, GPU or the RAM or the data center that is being built nowadays. Like, what do? They're doing this thing. I mean, I guess they are doing the prediction too, but the really, like computational intensive part for the model is actually the training part. So that is where your RAMs go. Like nowadays, RAM is pretty hard to find. This is where it goes. I want to update my weights and biases in such a way that my loss is minimized. Okay? In order to do that, there are ways to do. It's called backpropagation. And this is the technique that has been invented, like many years ago, like way back in our 90s, right? But it's still being used nowadays, even like the large language model, still using backpropagation to update the weight and biases, okay? This one is based on chain rule, okay? And in order to explain this, there's also another things that I kind of need to go over. It's called computational graphs, because backpropagation is more like a numerical methods for the chain rule. Okay, it's a way for us to implement the chain rule in a more computational efficient way. Okay, so that's the idea for the computational graphs. Okay, all right. You don't need to know this in full detail, but just need to be aware because the library that we will be using called PyTorch is built to solve this particular process. Okay, so it's good to know what it's doing, okay, in some details, okay? All right, so to explain what this is that computational graphs is dealing with how would you compute the gradient, okay? So the gradient is something that it comes from chain rule. The chain rule shows you this is the way to update your parameter through the gradient. And if you want to compute the gradient, in a more efficient way, then computational graph is a way to do. Okay, and then the way that the gradient is calculated, it's actually calculated backward from the output layer back to the input layer. So that's why this is called backpropagation, because of the way or the order of how the gradient is calculated through the computational graphs. Okay. Okay, I'm throwing you a lot of terms in here. Don't worry, it will be more clear once I go through this process, okay? All right, so I want you to imagine this. There are, the node is a function, right? This is the node in our layer, okay? And when you make a prediction, there are information that goes in, called AN, right? And the node is going to process the information. And we all learn that processing is linear transformation and the activation function, right? And then it's gonna split out the output called A out. Okay, so that is called the forward pass or the prediction pass. Okay, the things that we have done so far. Okay, but then during the training process or the backpropagation, there actually is gonna be another information that goes back. Hence the name backpropagation, okay? And that is called the gradient. So the gradient is just a number that you calculate in each of the process, okay, backward, okay? And you can think about this as this gradient is like an input on the training path, okay? And then it's gonna hit this node one more time, right? And this node is gonna do something to the gradient and then split out the gradient output, okay? Again, you can imagine this as another function, right? This is a function that takes in the gradient as an input, a number, and then output another number that we call the gradient output, okay? And the way this one is doing it's actually the gradient that is in output. It's going to equal to the gradient inside times the chain rule of the A that is output and then A that's the input. Or I would say the partial derivative of the A output and the A input. Okay, so again, you don't need to understand, why this comes. It can be proved that this is true, but I guess just take my word for it for now that this is a way to kind of simplify all of these calculations. Okay, all right. There are other ways to do, because this is a very simple node, meaning that one in and one out, right? But then there are also another, a slightly more complicated, because some of the nodes can accept two inputs, multiple inputs in a way, but then output just one output, okay? So in such a way, then you will start to have A in a different number, like A in 1 and A in 2, but then just one A out, okay? Again, if you go backward, it's going to be reverse, meaning that this node is going to accept one gradient input, and then they're going to split out two gradient output, okay? And the two gradient output is going to be equal to the gradient input for each one, right? This guy goes in here, same thing. But then I'm taking the output, again, see the output, right, here, but then with a partial derivative with respect to its own input in here. Okay, if I were to do this for the other one, probably it's going to be more clear. So the gradient output for the second, I guess the second gradient output is going to be equal to the input again, right, times the partial derivative of the output value with respect to its own input, like here. Okay, a little bit more complicated, but as you can kind of reason through it, that this type of pattern kind of makes sense, right, in terms of, how it should be, okay? And then there's another way that it can happen is if you only have one input, but then it goes out into more nodes. So imagine that there are more nodes in here, okay? Then things kind of, then the gradient part is going to have to be sum. So you're going to have two gradients input coming in, okay, and then one out. But then the output gradient is going to be, a summation between the first term, which is coming from the input, right, here. And as you can see, the pattern is always the same. So the out over in, right? So the partial derivative of the out over the in. But now we have two output, right? So that's why we have two A out, right? Something like that. Another one is also the same. So the input gradient and then the partial between the A output and the A input. Okay, so as you can see that the pattern kind of repeats, okay? Okay, so I know that this one is a bit weird, I know, but it will make more sense when we go through the whole, the actual process, okay? But keep in mind that there are multiple ways to calculate your gradients based on, kind of like the connectivity of your nodes, okay? All right, so let's try to train this network, shall we? Okay, and in order to do that, I'm going to add another node called the loss node. Okay, so this loss node is actually going to be just accepting the output from Y and output this loss. So this one is essentially the root mean, the MSE part, the mean square error that we calculated. So in particular, the things that we just calculate is something like this, right? This is going to be this part. So 5.082. In this particular example, this node is going to output this 5.082. Okay, so 1 is in here, output the loss, which is 5. Okay, so again, our goal is that if we can construct or have a way to change the weights and biases in here, such that whatever coming out from here is minimized. That would make sure that we have the good model. Okay. Okay, and the starting point for this is actually this part right here. Okay, so you can imagine that this particular L node, okay, it's going to accept the gradient. So you have to have, like, during the back propagation, you're going to have the gradient that goes from the last node back into the very input node, the very first node. Okay, so the gradient is going to go back from here to here. Okay, and the starting point for the gradient is 1. So I'm going to just starting with 1 right here. So this is my, like, first G in my computational graphs. Okay. All right. So let's do this one one by one, right? Shall we? So okay. So this L nodes in here, it's going to be the MSE parts, right? So what is the so first, what is the partial derivative of this L and y hat, right? Keep in mind that y hat is the A in, right? L is the A out. So this one is actually this picture over here. So this one is y hat. This one is L, right? So in order to find what the G out is, I need to know what is the derivative of the A out over A in, right? So that's going to be derivative of the L, right, over a partial derivative of y hat. So I need to know this partial. And we can do that because we already have the functional form for the MSE, right? So right here. I think it might be time for me to use my tablet, this, because it's going to get too ridiculous to write. Okay, so bear with me for a bit, okay? Okay, this is much better. Okay, so I want to calculate this one over here. Okay, how do I do this? So first, I want to go back. Oh, okay, I don't need this one. Sorry. Okay, let me see. I'm going to take this particular equation right here. Okay, so I can just write in here actually better. I want to calculate this one, right? Okay, so that's going to be, okay, so let's say n equal to 1. Because I only have one observation. Okay, so that's going to be partial of, you know, yi, right, minus y, so y minus y hat, okay, square y hat. And for the calculus Jedi over here, what is this? Okay, 2, right, and then y minus y hat. And then I think I need to have a minus sign. Right? I haven't done calculus for so long, but I hope this is right, okay? Okay, so let's take this one and go back here, okay? Would you agree? Wait, oh, okay, so the negative sign goes in here, so I switch the order, okay? So once I have this one, you know, the way that I would calculate my G out is that keep in mind that this is not symbolic math calculation. This has to be in computer. So in computer, we don't store variable, we store a number. So what I want in here, I don't want this thing. Like this thing, it's just symbolic math. I just need a number. So I'm going to plug in the real number right away. So that's going to be what? 2, right? Y hat is 10. No, it's not 10. Y hat is what? Right here, 7.745. Okay, so that's something that we calculate from the forward path, so prediction. Okay, so 10 minus 7.745, and that's, wait, I got it backward. It's actually 7.745 subtract by 10. And that should be about right. Okay, so as you can imagine that if I want to calculate the signal that goes out, the gradient that goes out, it's going to be equal to the G in, the gradient in, which is this one over here, times the partial of L and then y hat. But then this one is actually, you have to plug in the number. So we don't keep this variable in here. We keep number in the memory, in the computer. So what we're keeping is actually, we're keeping this number over here. So we record it in our operation that, you know what, the things that goes out from here is negative 4.508. That's called the gradient signal that comes out from this loss operation. Is it fun? But I mean, the moral of this is that it's actually not something that too complicated. Like once you kind of dig down into it, you will see that a lot of things, you know, that we do inside is pretty simple. But the sheer amount of it that makes it so complicated, right? And it's kind of amazing, like how just a simple thing like this can produce something like LLM nowadays. Pretty cool. Okay, anyway, I digress. Okay, so next up, this one, again, this particular node, it has one input and one output, right? So the computational graphs is going to be the same as this guy over here. Same thing. I want to calculate whatever goes out, the gradient out. I need the gradient that goes in, which we already know the answer in number, okay? But I need this partial. So what is this partial? Let's go back. This is going to be the partial of y hat, okay, over the z out, okay? But keep in mind that this particular activation function is just a mapping function because you were told that z out, okay, equal to y hat. Okay, the output node, the activation is just one-to-one mapping. So partial of y hat and c out always going to be equal to 1. Okay, so this one, very simple. So once I got this one, I can say that, okay, something that goes in, the gradient signal that goes in here. But then the gradient part, the partial derivative part is right here, which is 1. So again, my G out is negative 4.508. All right, and this number is going to be stored in the memory during the training process. Okay, again, we don't store the variable. This is not symbolic. This is numeric math. Okay. Okay, and the fun part begins now. Okay, so this one, you can imagine that there are many input, right? But then one output, right? So again, many input meaning that you have 2 input from here, right? And I can imagine that actually this input also come from the choice of weight and biases too. Okay, so the way that I visualize the graph is that, you know, this particular operation, which is a linear transformation, you need input from 5 things in here, okay? And it's going to output this z over here, okay? So the way that we will do is kind of similar to this page over here, this one. So this one has multiple input and 1 output, right? So when you calculate the output gradient, there's going to be many output gradient. Okay, so this one has 2 output gradients, right? But if you go back to this one over here, this one should have 5 output gradient. 1, 2, 3, 4, right? It can be like G1, G2, G3. I don't remember the order, but something like that, okay? So there's going to be G in, which is equal to negative 4.5. But then we're going to output 5 gradients. And this one is actually going to be useful because this one is going to be used to update the weights and biases now. So this is the part where we actually learn. Okay. Okay, so let's go to this slowly, shall we? Okay. So first, in order to calculate all this output, I need to know the partial derivative of all of the output with respect to all the input. Okay? So I need to know what is the partial of Z out with respect to any of this. So there are going to be five partial derivatives that I need. Okay, so you can verify one and take my word that the rest is the same. Okay, so for example, if I want to do Z out with respect to W2 out, what would it be, right? So this guy Z out, okay, with respect to phi. Oh, let's do phi first. Okay, let's make more sense. Okay, hold on. So let me do partial of Z with respect to, how about phi 1? Okay, phi 1 out. Okay, that's going to get, okay. I can calculate this, right? Because I already know the form of, the dependence of Z with respect to phi 1, okay? So what I'm going to do is this. I'm going to type this, and then W1 out, phi 1 out, plus W2 out, phi 2 out, okay, plus B out. Okay, so essentially I'm just copying the linear equation here, right? And all of this is going to be with respect to phi 1 out. I mean, it looks complicated, but just linear term, right? So the rest can be taken as a constant, right? So all of this goes away, right? All of this goes away. The rest is just W1 out. Okay, so as you can see that this one, okay, equal to W1 out. But wait, remember, we don't want to store symbolic math. This is not symbolic, right? This has to be numerics. So I need a value, like a number, okay? Do I know W1 out? Of course, I know it because I just mentioned it a while ago that W1 out is 4. Right? This initial value for the weight. Okay, so I know the value, so I'm going to keep everything in value. That's why this one equal to 4. And it's exactly what this one is. Okay, and now you can see the pattern, right? What about the partial of Z out with respect to phi 2? That's going to be the second weight, which is 5. So that 5 comes from that initialization table that I had before. Okay? But then if you do the partial of Z out with respect to the weights, then it's going to be equal to the phi out. Okay, so it's kind of switch the side, right? Okay, so maybe I'll do another one. Because this one is a little different, right? I'll do another one. Okay, now I want to do partial of Z out with respect to, now I want to do W1 out. Okay, so I want partial of this guy with respect to this guy over here. I want to do this pair, okay? So again, I'm going to plugging in partial of W1 out, okay, phi 1 out, okay, plus W2 out, phi 2 out, okay, plus B out, okay, and then that's going to be equal to the partial of W1 out. Okay, and again, the things that can be constant is this term, right? This one can goes away, this one can goes away. But then if you do partial of this term, then what's left is actually this guy over here, okay? So that's going to be equal to phi 1 out, right? Okay? Again, we don't store things in variable like this. So what is this phi 1 out over here? This one actually comes from the forward pass that we just did, okay? So during the forward pass, that phi 1 out is actually this one here, 0.811. You kind of have to refer back to where it comes from. So you need the forward pass though, in order to generate all of this number. So I need this 0.811. So this one, I'm going to go back and plug this one in here, 0.811, which is exactly what this number is, okay? I mean, that's where it comes from. Again, if you do the partial of Z out with respect to W2 out here, it's going to be equal to phi 2 out, which if I were to recall back from here, then it's going to be 0.899, okay? 0.899, which is exactly what this one is, okay? And then lastly, if I do partial Z out with respect to the bias, it's always going to be equal to 1, okay, because bias is just single term, okay? Okay, and that's probably the most complicated parts in this page, okay? If you kind of grasp the concept here, you pretty much solve the backpropagation, you know, okay? So the rest is just kind of matching all of these things together, okay? So you can refer back to how this thing is done in this page over here, okay? So it's going to be like this, okay? So I want the partial times the input, okay? So the respective partial times the input. That's all I need, okay? So I'm going to need, okay, so I'm going to need, for example, if I want the output, this G out, I'm going to need this respective partial, which is the partial between the Z and the phi, time the input. Okay, so I need this partial, which we already calculated, right? This guy over here, right? That's the partial between this pair over here. And then the input, which is negative 4.508, right? And that's it. And then we just plug in all the numbers. Like we don't need to store any variables in here. So negative 4.5 times 4, that's negative 18, okay? And also if I need the G2 out, right? So that's going to be from the partial of Z out with respect to the phi 2 out, which we already did, equal to 5, okay? And then the input, which is the negative 4.5, right? So that's going to be equal to negative 22, okay? So that is how we calculate whatever the output from the gradient. So this one, so these two output, it's actually going to go to the nodes that lies on the previous hidden layer, okay? So the layer on your left, okay? Yeah. But the kind of like even more importantly is actually the gradient that goes here. So this gradient that goes here, it's actually going to be the one that updates the weight and biases, okay? All right, so let's go through one, and you can take my word for it that the rest is true, okay? I want to see what the gradient G out here, right? Again, I need the partial between of the output and the input. So the partial of Z out and W1, we already did that. This guy is over here, which is 0.8, okay? times the gradient input, which is negative 4.5 again. Okay, so that's going to be negative 18. Okay, so this one goes here. Okay, sorry, actually, so this one goes here. Okay, and then so that happened. Again, if I do the G in, the G out of W2, okay, same thing. It's going to be equal to this partial and then the input, negative 22. Okay. And then you can kind of, wait, sorry, wrong one. This guy is over here. Sorry, get confused. Actually, this guy. Sorry, this guy over here. So let me write it one more time. I don't want you to point to the wrong one, okay? So I need the partial Z out with respect to W1. So that one is over here, okay? And then the input part is over here, okay? And then I got this number, okay? And the rest kind of follow the same pattern, okay? With the exception where for the biases, it's pretty simple, okay? It's just one. All right, so now we are at the meat of the topics now. So once all of these weight and biases got their gradient, okay, it will update itself, its value, okay, with this very simple update equation, which is the new one, take the old one, and then subtract it by the learning rate times the gradient, okay. So this is how I do. If I want to find what the W1 out, that is new, okay, that's going to be equal to W1 out O, okay, so the initial value, right, subtracted by the learning rate. So this one is another hyperparameter that you need to specify up front. So let's say 0.1. Okay, so let's see, I'll just write it like this, eta times the gradient. Okay, so the gradient, let me just write it as G W1 out. Okay, so let's plug the numbers in, shall we? So W1 out, O, right? That's going to be equal to the initial value that I specify up front. That's going to be 4. Okay? Subtracted by 0.1, which is the learning rate that we specify up front, times the gradient G W1 out. Yeah, it's going to be annoying to say this. Negative 3.656. Okay, and that's going to be equal to, hopefully, you can verify this for me too, 4.366. Okay, you can verify that, and if it's wrong, let me know. Okay, let's do one more time for W2, shall we? So that we are more familiar with this. So my W2 out new is going to be equal to W2 out old, subtracted by eta, and then now I need G W2 out. Okay, so that's going to be W2 old is going to be 5 subtracted by 0.1 times G W2 out is actually negative 4.053. 4.053. And hopefully that will be equal to 5.405. Hopefully. And again, with the bias, the same thing, you know, yeah. And as you can see that this is one backpropagation passed, right? And you can see right away that right now, our weights and bias has changed. And this is actually how the model learns. This is a learning process. You change the weights and biases, okay? So how do we do after we learn? One passed, okay? Okay, oh, and I just want to let you know that this equation actually can be derived from the chain rule, okay? So which I'm not gonna go into more detail, but again, and the way that you, I guess the theory behind this is called gradient descent. Okay, maybe I'll show you another figure. Okay, this is called gradient descent. Like the whole thing that you have been doing so far, gradient descent. Okay. All right. And as you can imagine that right now we have been talking for half an hour. We are only here. Okay. And we have updated 3 parameters. Right. We still have the rest of the network to update. But it's the same. It works the same way because remember, we already passed the gradient down the connection. So all of this gradient is gonna get changes from all of these activation nodes, right? And the gradient that goes into this linear combination is gonna get updated and gonna be used to update this weights and biases, right? But then there's also going to be another gradient that goes down the connection. And this gradient is also going to be used to update another weight and biases. And then go down until we're done. We don't need anything. So we don't need to go to this, okay? Because there's nothing to update, right? The reason that we go down the connection is because we want to update the weight and biases. That's all, okay? So in the end, if we were to do this manually, this is how we do, right? All of the weight and biases after one passed, then the weights and biases are now different. And if we were to calculate another prediction, okay, so that's going to be from x back into y hat again, but with the new weights and biases, then you're going to see that our prediction is going to go from 7.745. Remember, this one is the one that we had before. But with the new weights and biases, it's going to be 9.7. Okay? And remember that what we want is y equal to 10. So that means that our model is actually better. Right? And again, if you look into in terms of the loss, we have reduced the loss from 5 to 0.3. So that's a lot, right? We just one passed. We're almost, at the, we were much more accurate in terms of our prediction, okay? Okay, I would like to give you 10 minutes break, okay? And we'll be back. But thank you for staying with me. This is the hardest part. The rest is easier, okay? I always say that, but then it gets harder every time, I know.